Okay, in the last video, we were talking about stationary phases, and we were like, hey, well, SiO2 is pretty normal, and it's pretty common, so this is what I'm going to see most of the time, and when I do this, and that is what I use, then these are very polar surfaces that we are utilizing. So all of my polar components will stick to the polar stationary phase, and they will hang out, and they will madly fall in hubba hubba love together, and then sooner or later they leave and they go home and they spend the night at their own apartments or wherever they come from, and then they might see each other again the next day. And then they'll spend some more time, and then they hang out a little bit longer, and then there's going to be some relationships where it will see that polar compound, and it will look at it right off the street, and it will go, I hate you, and then they'll take off running. So those will zoom through the silica. They will not stay behind. The silica does not reach out and grab those and try to make a relationship with them. They'll just keep zooming on up the plate in this type of situation, and they will try to get away from the stationary phase as much as possible. So with the silica, we said that there is a layer of OH groups that are on the surface of these particles, and those are alcohol groups that we see that's going to be on the surface. Then we also said that this can be modified in a number of different ways, and this is through the protonation of alcohol groups, and that is based on kind of the basics of organic chemistry. So if you've taken chemistry, probably 252 is when they go in and talk about alcohol reactions and what this thing is doing. That's kind of when that takes over. So that is probably when you'll see it. Maybe you've taken Orgo 2, maybe you've not. If you've not, don't freak out about it. It's not an organic class. This is an instrumentation course. And I like to throw in some organic for those people that have taken the class, just to make all of the pieces somewhat start connecting together. So if the component interacts with the OH group, that is great. And we start to see some laggy. We start to see some areas here where these components are going to hang out and they're going to create a little bit of drag. And that means they're just going to be held back a little bit longer. But this is only one part of the story. So polarity is great. And this is one of the things that I use to determine how things separate. All right. That's what this is all about. And there's actually other things that are going on too. It's not just polarity driven. There's other things that are going to be present, and we need to talk about some of those. So another thing that can be used to help our decision on how these things begin to separate on the silica plate are going to be some of the different types of bonding that we can see take place between the components that I'm trying to separate and the silica as well. So for instance, the silica we just said had OH groups that were hanging off of that. And this sets it as a prime example for what we call hydrogen bonding. So you're going to look at this and you're going to go, oh, well, there's a hydrogen bond. There's a hydrogen onto the oxygen. No, there's not. There's not. So that hydrogen is connected to the oxygen, absolutely, but that is not the definition of a hydrogen bond. The definition of a hydrogen bond, and I'm going to do this in a different color. The definition of a hydrogen bond is a hydrogen that is on an N, an O, or an F that is attracted to another N, O, or F on another molecule. All right, so this is meeting one half of that definition. There is a hydrogen that is attached to an N, O, or F. Now, what this means is that let's say that I get a component and that component has another, I don't know, oxygen, right? So let's just say an OH group on that one as well. And I'm just going to do an R for something random. It can be anything random, not rebound. So this hydrogen is attracted to that oxygen. There is a bond that is present, but that oxygen's very, very greedy. I mean, if this was a relationship here and they shared a bank account, oxygen's going to control the money, and it will not give hydrogen anything at all. It will just take it all away, and it will be like, no, I'm not getting you nothing. And oxygen might just be sitting at home, and oxygen might not be working at all, and oxygen just might be sitting around calling the shots because that's how that relationship works. Either way, it's very electron greedy. It's very money greedy. All right, well, that oxygen, or that hydrogen, sorry, is going to look at that other oxygen, because that is another NO or F, and it's going to be like, hey, I'm in this relationship right now with this oxygen, and I know that you might be the twin, but I kind of really am attracted to you, and I'm wondering if you're going to do me and treat me any better. And of course, that's not going to happen, but hydrogen doesn't know that. I mean, those oxygens grew up in the same family, they had the same values. So that hydrogen is attached to an NO or F, and that hydrogen is attracted to another NO or F that's on another molecule. So whether that was OH, or whether that was maybe like an NH2 group, or maybe that was just a fluorine that was hanging off, I don't know, it doesn't matter, but that is the definition of a hydrogen bond. So the second thing that we've got to do is kind of go in and say, listen, there's other things than polarity that is at play, and another thing that can go on is some type of bonding situation. And in this case, hydrogen bonds can play a very important role in how the molecules lag behind. Because if the hydrogen bonds are present, those compounds are going to drag a little bit more. They're going to have more effort that you're going to have to put in to push those through the stationary phase and kind of toward the top of the plate or out the other end of the column. So that is just one. Another one of these are called dipole-dipole interactions. Dipole-dipole is the idea that I get a molecule and I get another molecule, and what happens is that these are permanent types of charges. So I get a positive on this side and a negative on this side. So they are there, they are localized, they are not moving, they are present. I mean, think about like magnets, for example. That's how this process is going to work. So there is one dipole on one molecule, and then another dipole on another molecule is going to take place right there, and they are going to magically fall in love. And when they do this, they create a bond, and that bond is going to happen in between them, and that bond is like extra glue that keeps those molecules interacting together. So yes, polarity is part of the story, but out of the polarity is going to come all of these other concepts like hydrogen bonding. Is hydrogen bonding there? Because that's going to increase the way that these two components are going to interact with each other. Is dipole-dipole there? Because again, it's going to increase the way that these molecules interact with each other. Another type of bonding that we can talk about here is London dispersion. And London dispersion is the idea that these charges are not necessarily localized, but it's the idea of temporary forces that begin to happen. So what goes on is that these electrons are there, and these electrons will move. And as they move, they spin round, round, baby, round, 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 and they go around and around and around and around and around. So as they spin and spin and spin and spin and spin, there is a statistical chance that electrons will become lopsided on one side of the molecule. And if electrons go on one side of that molecule and they create a temporary charge, well, electrons are negative, so they would create a temporary negative charge. Then what goes on is that it starts a domino effect, and it starts affecting the other molecules that are around it. And it's like, oh no, oh no, oh no. So all of these other molecules kind of rearrange everything that they're doing because of what they see that's incoming. And what that incoming thing is a temporary negative charge and a temporary positive charge that has been created due to the electrons moving throughout the entire molecule, because that's just what they do. So and that's the way that I kind of want you to envision this, at least. So if this is what goes on with these molecules, that is called London dispersion, because this is not going to stay around very long. Electrons are going to continue to move. Electrons are going to be continuing to spin. If there's a domino effect that happens, though, it slows it down, and it doesn't really want to kind of change up too much after that, but it can easily be broken and split and kind of taken apart. That's not a big problem at all. So dipole-dipole interactions, hydrogen bonding interactions, and this randomized London dispersion is going to take place as well. London dispersion typically we say happens to all things, and the reason that we say that is because electrons are constantly moving in these molecules, and they never slow down, they never stop, they're always kind of swarming around like a big old cluster of honeybees, and it's just the way that they are. And sometimes those bees are lopsided on one side of the garden versus the entire garden at one time to make it very smooth. So there's another reason that separation begins to happen. London dispersion takes place as well. So most compounds are going to interact with the stationary phase in more than one way, and it could be straight up polar interactions, absolutely. But these non-polar molecules that are there, they could actually start participating in some of the other bonding. So just because something's non-polar doesn't mean that it's going to drastically race up the plate or through the column. It's going to go fast. Absolutely, it will go fast. But we start to see differences in how these components interact with the stationary phase because they all are contributing in a different way depending on the structure or the compound that they have made that they find their home with. Next up, another thing that can happen here, number 5, is pH. These molecules are pH dependent, and the separation is also pH dependent. So I'm going to give you an example here. One of the things that we will probably do in the course, if you've not done it already, is a paper chromatography of amino acids. So this carbon is going to be involved in a carboxylic acid group, and it's also involved in an amino group. And in acidic conditions, we are going to see that that amine group, which is normally NH2, is going to be protonated because it is a base and it loves some hydrogen whenever it can get its hands on it. So under a certain pH level, this is kind of what goes on, and the pHs that we have, whether it's 2 or whether it's 7 or whether it's 10, who knows what the pHs are going to be, that can start affecting the way that this molecule is going to be operating. So that carboxylic acid is an acid, but this carboxylic acid group will only spin out the proton after we go above a certain pH. So at pH of 1, it's COOH. Nothing kind of fancy happens here. And that COOH group, well, because of that, that could maybe participate in a hydrogen bond because that hydrogen's attached to an N or F. And if it sees another group, okay, absolutely, like silica, woohoo! All right, well, here we go. Okay, at pH of 2, it's probably still COOH. And then when we go to pH of 3, there is a chance that this carboxylic acid group begins to spit off some protons here. And then as we go to pH of 4, and then as we go to pH of 5, and then as we go to pH of 6, absolutely, that pH is going to determine how this molecule begins to start changing. And now all of a sudden, we don't have straight up hydrogen bonds, but now we actually have a full-blown negative charge due to the deprotonation that has happened at the carboxylic acid level. So now we are talking about different interactions, different ways that that molecule is going to be going in for the kill with the silica. And then as we start increasing the pH and as we starting to get into pH of 7 and pH of 8 and pH of 9 and pH of 10 and blah, 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 eventually what we'll see is that that NH2 will also lose a proton. And when it does that under certain conditions, then all of a sudden that positive charge that was there now just kind of completely disappears, and we go to an NH2 amine group. And that now is not a charge any longer. So now that pH really changes that molecule, and the way that it interacts with that silica on the stationary phase is totally different than what it was at pH of 7, than what it was at pH of 1. So these are the things that we have to keep in mind as far as how things begin to interact with a polar stationary phase or non-polar stationary phase, actually, because it's all about interactions with something. And if I'm making these changes, and pH is one of those changes, it is changing the basics and the foundations of how these molecules begin to interact. So Polarity is very important. Hydrogen bonding is very important. Dipole-dipole is very important. London dispersion is pretty important with everything. And then, of course, the pH levels of some of these compounds are going to be important as ones. All right. So when we say polarity, I need you to understand that polarity is just really kind of the first thing that we talk about. It's kind of the priority that we always just blurt out. It's kind of the first thing that we go to when we make these decisions. But folks, these components can have similar polarity values. And if they do have similar polarity values, then why are they beginning to separate on the silica plate? If they're the same polarity value, shouldn't they be traveling up the plate at one time in one big blob? And they could, but then at the same time, there's other pieces to the puzzle. And now you've got puzzle piece number 2, 3, 4, and 5. These are things that we can do that if they do have the same polarity values or really close polarity values, well, these other kind of interactions are going on at the same time. And this is why things are beginning to separate out from one to the next to the next. So in the next video, we'll pick up from here. We'll talk more about stationary phases and how things interact with them, and probably keep adding to the list a little bit before we move on and talk about the mobile phases of the TLC and HPTLC slides or plates that we're using.